Hello, today we're going to go over section 5.6, which is composition of functions. Remember, we have our objectives or targets in this case. I can evaluate a composition of functions. I can find a composition of functions. I can state the domain of a composition of functions. We're going to explore the following topic. We have the formula below represents the temperature F in degrees Fahrenheit when the temperature is C degrees Celsius, and the temperature C when the temperature is K Kelvin. So these two are my formulas or functions. And A, we're going to write an expression for F in terms of K. So the first step in this case is going to be, I'm going to write the formula for the Fahrenheit because they want to write an expression for F. So I'm going to start with F equals to 9/5 C plus 32. That's going to be my first step. And now remember that they want an expression for F in terms of K. Who got K? The function C. So what I'm going to do here is, this is equals to 9/5. And instead of C, I'm going to open a parenthesis. And I'm going to make the substitution of K minus 273 plus 32. Okay, now we're going to simplify. Okay, we're going to apply distributive property inside the parentheses. So I have 9/5 K. And now if I multiply 9/5 times 273 negative, I'm going to get 2000. This is negative 2457 over 5 plus 32. Now we need to subtract because this one is negative, this one is positive. You can use a calculator, and what we are going to get in this case is 9/5. This is a 9. K minus, this is going to be a minus 2297 over 5. And remember, this one is the Fahrenheit. So that's the solution to numeral A. So we just did kind of a substitution, like the system of equations, and then apply distributive property and solve. So let's move to B. What is B in this case? Given that the function fx is equals to 9/5x plus 32 and gx is equals to x minus 273, now in this case they change the variable, write an equation for f of g of x. That's the way we're going to read it. F of g of x. What does f of g of x represent in this situation? So we're going to proceed with exactly the same steps that we did in A. Now, in this case, we're going to have, look at the notation. The notation is going to be different. So I'm going to use the black one. So I have f of g of x is going to be equals to, so I have f of x, okay? So I have f. And now I'm going to do the composition of that function, plugging in gx. What is gx? X minus 273. So I can open a parenthesis here, okay? And I'm going to write x minus 273, okay? So I have that one. And now remember, what is the function f? Is 9/5x plus 32. So now I'm going to do, this is equals to 9/5, and then I'm going to have x minus 273, and then remember this one is plus 32. We already solved this one. The only difference from A is just the variable k. So this is going to be equals to 9/5, and then x minus 2297 over 5. And this one is just my f of gx, or composition of those two functions. Now remember, what does f of gx represent in this situation? So in this case is the temperature. in degrees Fahrenheit. As a function of the temperature in Kelvin. Okay, in Kelvin. Let's do C in this case. Water freezes at about 273 Kelvin. Find F composite of G of 273. Does your answer make sense? And explain your reasoning. So in this case, what I'm going to have, according to the notation, is F of G of 273. Remember that all these questions are related, so we're going to keep an eye on these functions that they're given to me. So what I'm going to do, this is equals to 9 over 5. And remember that instead of x, I'm going to plug in the 273. So 9 over 5 times 273. And I'm going to have minus 2,297 over 5. Now, if we plug in this one in the calculator, I'm just going to do this one in the calculator. This is going to be equals to 32. Okay, 32. Now, does it make sense? Yes, it does make sense. Yes. Why? Because the water, in this case, freezes at 32 degrees Fahrenheit. Okay, 32 degrees Fahrenheit, which is 273 degrees Kelvin. Now look at the graph. We're going to interpret the point shown in the graph. So I have a point here. The only thing they are giving me is x, and they are giving me y. And I have a straight line, and the point is 373 and 212. So that means this one is my value in x, this one is my value in y. So I have 373 in x, okay? And then I have my y value is 212. Now, 373, in this case, Kelvin, is equals to 212 Fahrenheit. Now, that's the temperature of boiling water. So that's what, in this case, the interpretation. That's the temperature of boiling water. Okay, that's it. That's the interpretation. These two are the same, and that's the, in this case is the temperature of boiling water. Now we have the formal idea of the composition of functions. Remember that the composition of a function g with a function f is, so we're going to create a new function hx, which is equals to g of fx. Again, let's keep in mind that this is going to be like substitution. We're going to plug in a function into another function, and the domain of h is the set of all the x values, such as x is in the domain of f and fx is in the domain of g. We're going to explain that one with example. We have a diagram here. So you have your input of f, okay, in this case is x. So the output of x, whatever is coming out of the fx, is going to be, in this case, the range of f. Okay, so I have the domain of f. This is the range. Now, but remember, it's a composite function, so this f of x is going to be the input of the function g, which is the domain of g. And then what we're going to have is the output of g, which is, in this case, the range of g. So it's like a machine, So you have your x, and then you are going to have fx, right? This is your output. And then you take this function, okay, and then we're going to plug it into the g. So you take this one, and then you have g, right? And then plug it in this function, you're going to have g of f of x. Okay, that's how it's going to be working. We have some examples that we're going to use. So I have f of x equals to the square root of 2x plus 1, and gx equals to x squared minus 4. Find the indicated value. So the first example that we have there is f of g of 4. Now keep in mind, remember that whatever is inside the parentheses, that's x. So you have x is equals to 4, right? And the function that is inside the parentheses is g. So I can easily, in this case, just find the value of g of 4. So 4 to the second power is, in this case, 16 minus 4 is equals to 12. Now, but with the notation, how is that going to work? So we are going to have f, okay, of, remember, g of 4. So I have 4 to the second power minus 4, close parentheses. I know 4 to the second power is 16 minus 4 is 12. So now I have f of 12. Okay. And now remember that f of 12 is just evaluating the function f of x. So I have fx, or f of 12 in this case, is equals to the square root of 2 times 12 plus 1, which is equals to 2 times 12 is 24 plus 1 is 25. So I have the square root of 25, and the square root of 25 is equals to 5. So that's my first solution. Now I go to B. I have f of g of 2. So in this case, I'm going to have f of, I have g, which is 2 to the second power minus 4. That's g of 2. And then I have f of 2 to the second power is 4 minus 4 is 0. And now I'm going to plug in here. So I have that f of 0 is equals to the square root of 2 times 0 plus 1. Okay. And the 2 times 0 is 0 plus 1 is 1. So this is equals to the square root of 1, which is equals to 1. Okay. Let's do C. I have g. Now, this one is the same function. It's g of g. So g of negative 2. So I'm going to find, in this case, g of negative 2. I'm going to use parentheses. Negative 2 to the second power minus 4. Okay. And then I have g of 0 again. Now, the difference to the previous one is that 0 was being evaluated in f. But in this case, I'm going to re-evaluate in gx. So I have g of 0 is equals to 0 to the second power minus 4. 0 to the second power is 0. And then minus 4 is equals to negative 4. And that's my solution. Last one, I have g of f of 1. So now I'm going to use f of 1. So I'm going to have g of, in this case, the square root of 2 times 1 plus 1. Okay. And then I'm going to have g of 2 times 1 is 2 plus 1 is 3, square root of 3. Okay. Square root of 3. And now I'm going to evaluate this one in gx. So I have g of a square root of 3 is equals to square root of 3 to the second power minus 4. Remember that this square is going to cancel the radical. Going to get rid of that radical. So what I have here is 3 minus 4, which is equals to negative 1. And that's the solution to this example. Let's move to example number 2. In this case, it says finding composition of function. So we're going to find now the composition of function. So example A says let fx equals to 5x to the negative 1 and gx equals to 3x minus 3. Perform the indicated composition and stat the domain. So number 1, f of g of x. So what I'm going to have here is f, the function f, okay, which is gx, which is 3x minus 3. 3x minus 3. Now remember that the function fx is 5x to the negative 1. So I'm going to have 5 times, in this case I have 3x minus 3 to the negative 1. Now we have a problem here. We cannot apply the distributive property because the exponent is negative. But if we use the property of exponents, if I have m to the negative 1, this is equals to 1 over m. Now in this case 5 will not go to the denominator because 5 is not elevated to the negative power. So in this case my solution is 5 over 3x minus 3. Okay, that's going to be my solution. Number 2, in this case I have g of fx. So I have g of 5x to the negative 1. Okay, I know that gx is 3x minus 3. So this is going to be 3. X is going to be the 5x minus 1, 5x to the negative 1, and then minus 3. Now here we can apply the distributive property because 5 is not to the negative 1. 3 times 5 is 15. X to the negative 1 minus 3. Now x to the negative 1, we apply the property. So we have 15 over x minus 3. When we finish the last problem, we're going to do the domain of the functions. We're going to go over the domain of the functions. So in this case, I have f of fx. So I have f of 5x to the negative 1. And remember, 5x to the negative 1, I have, so 5, parentheses, 5x to the negative 1 to the negative 1. Now, what is happening here? The properties of exponent in this case, if you have a times b to the n is equals to a to the n, b to the n. So this one is equals to 5 times 5 to the negative 1. Now here, negative 1 times negative 1 is positive 1. So this one is going to be just x, okay? And 5 to the negative 1 is the same as having 5, this one, over 5x. And 5 divided by 5 is x. And that is my composite function. Now we're going to do the domain. Now let's observe the first one. Okay, let's observe the first problem, the number 1. I know I have that denominator, and we cannot have a number that makes my denominator 0. So let's observe this one. I have gx, which was my composite function. So if I make x equals to 1, all this function gx is equals to 0. And 0 will make, in this case, 1 in this case is going to make 0 my denominator. So in this case, my domain is all real numbers, okay, except x equals to 1, okay? Because in this case, g of 1 is equals to 0, and this 0 is not in the domain of x, okay? It's not in the domain of f. Now let's observe this one, okay? Number 2, I can see this x in the denominator. So in this case, it's going to be, the domain is going to be all real numbers. The domain is all real numbers, except x equals to 0. See that? X equals to 0, because it's not in the domain of f. Because if you look at this one, x to the negative 1 will make that function f not defined at x equals to 0. And final, this one, it seems that the domain is all real numbers for this function. The problem is we have this fx here that, remember, it wasn't defined to x equals to 0. So this one, we also going to say that the domain is all real numbers except x equals to 0, because it's not in the domain of f. So we need to be very careful with the domains of those functions. Okay, let's move to the next example. In this case, we're going to have part B, okay, part B, we have let fx equals to 2x squared plus 3x minus 4 and gx equals to x plus 3. We are going to perform the indicated composition and we are going to state the domain. Function number 1, I have f of gx. So what I'm going to do, see that gx is x plus 3? So I'm going to have f of x plus 3. Okay. Now remember that the function of f is 2x squared plus 3x minus 4. So I'm going to have 2, in this case, x plus 3 to the second power plus 3x plus 3 minus 4. Minus 4. Almost made a mistake there. Minus 4. So now remember, for this parenthesis, I have that a plus b to the second power is equals to a squared plus 2ab plus b squared. Or you can split that parenthesis as x plus 3 times x plus 3 and do the distributive property. It's up to you in this case. So what I'm going to have here is 2 times x to the second power, that's the first element, a to the second power plus 2 times a, okay, 2ab, so 2 times a, 2x, times b, which is 3, and then plus b to the second power, 3 to the second power. This one is just a simple distributive property. 3 times x is plus 3x, 3 times 3 is plus 9, minus 4. And now I apply the distributive property. This is 9, okay? 2 times x squared is 2x squared. 2 times 6, 2 times 3 is 6, and 2 times 6 is 12 plus, in this case, 12x. And then I have 2 times 9 is 18 plus 3x plus 9 minus 4. Now I'm going to combine like terms. So I'm going to have 2x squared, 12x plus 3x is plus 15x. Then I have 18 plus 9 minus 4 is 23 plus 23. And that's what I'm looking for. We're going to give the domain at the end of this example, okay? So let's do the second one. G of fx. So in this case, I'm going to have g of 2x squared plus 3x minus 4. And remember that g function is just x plus 3. So what I'm going to have is 2x squared plus 3x minus 4 plus 3. So in this case, it's just 2x squared plus 3x minus, in this case, negative 4 plus 3 is negative 1. Now, the domain for those functions. For the domain of the first one, as you can see, I have f of gx. So gx is all real numbers. The domain is all real numbers. There is nothing that interferes with the denominator. Same for the function of f. So in this case, the domain is all real numbers. And as you can see, this one is just exactly the same. So the domain is all real numbers. Now let's move to example number 3. We're going to model in an application problem. And it says that the function c of m equals to 15 minus 10.5 m approximates the temperature in degrees Celsius at an altitude of m miles. The diagram shows the altitude of in this case in miles of an airplane t minutes after taking off, where 0 is less than equals to t, less equal than 30. Find c of m of t. Evaluate c of m of 30 and explain what it represents. Okay, so I'm going to start with my function. So I have c of m of t, okay, which is equals to, I'm going to put the problem here, which is equals to, in this case, c, remember, m of t in this case is, we had it here, 0.2t. So it's have 0.2t. And now I'm going to evaluate 15 minus 10.5 times m, which is 0.2t. So I have this is equals to 15 minus 10.5, and then times 0.2 t, and then we apply distributive property. Negative 10.5 times 0.2 is negative 2.1, so it's 15 minus 2.1 t, and then I'm going to, this is my function, the composite function. Now I need to evaluate c of m of 30, so I'm going to have c of m of 30 is equals to 15 minus 2.1 times 30. Negative 2.1 times 30 is negative 63, so it's equals to 15 minus 63. In this case, 15 minus 63 is equals to negative 48. Okay, so in this case, the answer, remember, it's an application problem, and it says, in this case, the diagram shows the altitude, yada yada, find c of mt, evaluate, and explain what it represents. So in this case, I'm going to have here, so c of m of 30 is equals to negative 48, which indicates in this case that after 30 minutes, the airplane is at an altitude that has a temperature of about negative 48 degrees Celsius. Okay, that's what it means. That's how we can interpret or explain the reasoning of the problem. Okay, this is the last example we have for this section. I hope you have a wonderful day. Any question, and you can let me know.